Okay, hello everyone. Today for lecture 11, we're going to be talking about choosing a database. Last time we talked about distributed database consistency, which I think was our second lecture on distributed NoSQL databases. And we saw there that we need to think about more than just how to distribute the data to get horizontal scaling. Once we partition the data among many different nodes, we have if we use a simple design where the data is just in one place, we can get scalability, but we have some reliability problems, right? If the data is all in one place, then if that machine fails or is unavailable, then the system either loses data or is not available for that time. And if you have a system, if we're scaling this out to a large size where there are a lot of these nodes acting horizontally together, then the likelihood of a failure is very high, so we need to definitely deal with this issue. We would expect there to be failures every day, for example, in a big system on at least one of the nodes. All right, so we want to replicate the data then. The simple way to do that is to store a copy of the data in, let's say, two other nodes, or one other node. But in most of the examples I gave, I showed it in three other nodes because of the additional reliability it gives you. When you do that, though, the key thing is that introduces consistency problems. So now, instead of having the data in just one place, every piece of data is in three places. So when we write, if we're changing that data, it'll get changed at different times in the three different locations it's stored. And there's a theoretical result called the CAP theorem that proves that you can't have consistency of data, availability of data, and partition tolerance at the same time, where partition tolerance means that it's a distributed system where, meaning that it can be, in the sense that it can be, the nodes can be separated and unable to communicate with each other at some times. If we have a totally reliable network with no delay, then it's easy to get consistency and availability, but in general, a real distributed system, if you're really deploying this on a network, on the internet, you're not going to have that instant communication and reliable communication. We defined some rules for what we mean by consistency: monotonic reads, monotonic writes, and reader writes. Reader writes is a good simple example to remember that makes sense, right? If a single client, this is from a single client's perspective, if that client writes data and later reads back data, it should get the same value that it wrote, or it should get a newer value. When you combine these three properties, there's a definition of consistency called linearizability that is useful, and it's not too strong, but it's also strong enough to build real systems. And this is where you have a bunch of individual actors. They all perform actions. In different parts of the distributed system, we're not guaranteeing that all the different actions take place in the same order because there are delays when the actions reach different parts of the system. So we don't want to guarantee strict consistency or strong consistency where everything in all the nodes happens at the same time, like data is always written in the same order and read in the same order. Instead, we just guarantee linearizability, which means that the partial ordering of the actions that take place in the different clients is preserved in all the observations of the actions across the system. So when those actions are serialized, in other words, when a given actor is observing what the system does, it sees the sequence, and if you take the parts of that sequence and attribute them to the actors that generated them, those actors should agree with the ordering that the subset that they subset of actions that they initiated. They should agree with the ordering that appears in that total ordering, where you take everyone's actions and put them together. It's called linearizability. Okay, right. So those are some definitions of consistency. So in order to guarantee that, we found that the general way that distributed databases do that is by creating some kind of rules for waiting when appropriate, when the system is not yet consistent enough to wait. We saw that there was a problem. We saw some examples where if you have three replicas and you, let's say, write to one of them, but then read from a different one, if you do that too quickly, the write that you made to the one node might not have propagated to the node that you later read from, right? So that violates the read your writes property. And somehow waiting until everyone gets the data, or enough of the nodes get the data from that first write would have solved that problem, right? So the way that we introduce weighting usually is by defining some kind of quorum level, which can be different. And this is like the number of nodes that have to acknowledge or respond to your reads or writes before you can proceed to your next action. Again, we're dealing with client level consistency, so what matters is whether a single client's sequence of, let's say, read and read or write or read after write, whether that makes sense. So if you slow down the second action, if you slow down the first one so that you can't proceed to the second one until the system is synchronized enough, then you can get consistency. And with all level quorum, you require all the nodes to respond. That kind of slows you down a lot, but it makes the system very consistent. And then later on, you could, if let's say you're writing with all and then reading from one, that would be okay because anyone you choose would have all the data. But a useful trade-off design is to have a majority quorum where you write to node. When you're writing to nodes, you wait for a majority to respond before you move on. And similarly, when you read from nodes, you wait to get a majority of responses, and then you choose whatever response. In most cases, those responses are going to be the same, but in cases where they're different, if you choose the one with the most recent timestamp on it, then that'll be guaranteed to be the most recently written value. And so with these quorum levels, different databases either have hard-coded different policies for quorum levels, or some databases like Cassandra let the programmer choose every time they do a read or write what quorum level you want to achieve, you want to use. So this lets you kind of choose dynamically whether you want reads or writes, or really to choose for different parts of the data, like whether you want to prioritize reads or writes to be faster, depending on whether you choose all, majority, or one level of quorum. Okay. All right, so now moving on to choosing different kinds of databases. Now remember that databases solve a bunch of different problems like scalability, persistence, indexing, concurrency, analysis, separation of concerns in the sense that by having a separate database, we can use an off-the-shelf system to handle a lot of the stuff that a lot of apps need, but then have just like the business-specific code in your app and not have to reinvent the wheel and rebuild all this database stuff. When in the different databases we're going to be looking at today, the main differences are in the way indexing is done, and in some extent the kind of analysis you can do. They all are persistent, and some of them have different scaling properties. Okay, so this is a table I think is a useful reference, and we're gonna go through every one of these rows today to explain. This is my rough definition of 8 categories of distributed storage systems, and of storage systems, I guess. Some of them are not really truly distributed, but anyway, they all have different characteristics. And I have some examples for each one that are popular that you'll see mentioned a lot in industry and also in research articles. So usually as a programmer, it can be a difficult choice to choose one of these databases to handle everything in your system. You might need to have more than one database. On the other hand, you don't want to have 5 different databases probably in a simple application, because that means that you have to maintain 5 different systems and you have to have 5 different ways of fetching data and writing data, right? So there's a little bit of a trade-off there between choosing one database or a small number of databases, and then kind of like shoehorning all of your use cases, making all of your use cases work in that one database, even though that one database maybe doesn't fit every use case you have perfectly. On the other extreme, you can choose the perfect database or the best database for your particular data type. But if you have lots of different data types, I mean, you would be choosing different databases for every type of data, and then that would add a lot of overhead in the management and kind of coding of the interfaces to the databases. There's another extreme also where you look at the available databases and you say, well, none of these are really totally perfect for my data set, and I have a lot of money and engineers around, so let me build my own database, right? If you're a big company like Google or Amazon or something, maybe you could do that. But we're going to be focusing on, in this class, on choosing from available databases and kind of studying what makes them different and why they were even invented or built in the first place when there were already existing databases around that kind of solve almost the same problem. Okay. So yeah, we'll go through each of these. This is kind of a reference. I'm going to show it again at the end, and we're going to go through them kind of one at a time and also define some subcategories. The first one, though, so that very first row in that summary of different databases was SQL relational databases, which we talked about at length already, but I just want to remind you of what these are good for, because you shouldn't ignore them. They're not the most scalable choice because writes have to happen on one master machine unless you do some kind of sharding, but like I've said before, sharding is difficult to do, and it complicates your design a lot. So sharding is an option to make it scalable, but like that, it's not, you don't get sharding for free. There's a cost to using sharding. So you kind of have to, when I think about relational databases, I usually don't assume that sharding is going to be available, because usually it's only in very specific cases when you can take advantage of sharding and not make it a real burden for your system in terms of the code base being really complex with, like, dispatching multiple queries and then manually sticking the results back together, right? That's a difficult thing to do in general. All right, so but with relational databases, as a review, the data is organized into many different tables that have predefined columns and their foreign keys that cross-reference. The nice thing about that was that the data was normalized, and with that, the benefit that gives you is that you can have data in one place that's referred to from many other places, and that allows you to change it in one place, allows you to have a very efficient representation. And you get transactions. Because all the data is in one place, it's very easy to have a bunch of things happen all or none. Like, and I'll talk more about transactions later in the next few slides. And finally, with these relational databases, you get to use the SQL language to run data analysis. And you might think that having to learn a second language in addition to whatever language you're coding in is a burden. But actually, first of all, it's not that complicated. And secondly, it provides a huge benefit in the performance of your analysis, and also the fact that you don't have to implement a lot of the functionality yourself. But when it comes to performance, this is beneficial because you could send a query to the database. Like, for example, this one here gets the average price and for every category of products in a database. So there are many products that all have different prices. They have categories labeled. So there's some kind of like grouping that happens where you separate the products into buckets, and then you sum up within each bucket, and then you divide by the total, right? So it's not hard to write that code, but this one line of SQL does it for you. And more importantly, the code gets executed on the database. So you send this one small query to the database runs that code. It looks through the data to get the answer, and then you get the answer back, which is going to be short. So the amount of data that's transferred back and forth and the latency is really minimized. Whereas if the data was, data is remote in a database, if that was some kind of simple key value store, you would have to, and you're implementing this like in your own code, like say Java or JavaScript or Python or whatever, you would be fetching individual pieces, like individual product information, and then piecing it together and doing a calculation. So you'd be transferring a lot of data back. So you'd be putting a lot more load on the network. There'd be a lot more delay because there'd be like a lot of these round trips to like, okay, let me get some of the data, analyze it, and that tells me I need to get some more data. The database is also doing that work when you give it the SQL query, but it can do that work in the same location where the data is stored. So the delay of all those operations of fetching data is like happening within the machine instead of over the network. So it's a lot faster. Okay. So that, I have said all these things before, but I think they're really important to remember. So it's worth repeating that. So if you like the way that SQL relational databases organize data into tables, you like having the SQL language available, you like transactions, and even if you have a lot of read load, like a ton of read load, like Wikipedia, you can still use a relational database and make it scalable with read replicas, although there'll be some delay between writes and reads, so that you kind of lose a little bit of consistency there. So this is a good choice where you don't need a ton of scaling, but and you're okay with, or maybe you even like, the rigid structure that the tables give you. Okay, so I mentioned transactions as being a benefit of relational databases because the data's in one place. It's easy to kind of lock data. So we'll see what that means in a second. But here's an example of a transaction. So it's a sequence of like three operations that have to happen together. And so what this is from a like online shopping example, where these are all SQL commands. I'm not quite sure exactly. I think this is for the MySQL variation of the SQL language. But anyway, so you start a transaction, and then here we're actually storing to a temporary variable a new order number that's going to be used. And the way we get that is by picking out from this orders table the maximum order number that's already there and adding 1 to it. So we check it at the table, get the maximum order number, add 1 to it. That's our current order number. And then the next command, so this is a second query, creates an order using that order number we just calculated, as well as some information about the order, like the date that it was created on. Okay, so we've created a new order record. And then finally, we're going to add some order details, which are like the line items for that order. So this order contains, let's say, 2 products that were purchased. So we're going to add those to the order. So these are 2 rows that are added to a different table. The table is called order details. Of course, it has a foreign key order number that refers to the orders table. But there are three rows that need to be created, right? The order that has the basic information for the order, and then 2 different products in the order details. Those 3 things together apply to the order. And this is all in a transaction. Start transaction, and then finally commit, which ends the transaction. And remember, so the point of a transaction is to make all of these steps happen atomically. What that means, this is really covered well in the operating systems class, and one of the reasons, in my opinion, the most important reason to take an operating systems class is to understand locks, concurrency. That part of the class is really essential for programmers across the board, no matter what kind of programming they're doing. And I've taught that class in the past. But anyway, but if you haven't taken that class, what it means to execute a set of instructions atomically means that even though the system has some concurrency, like in other words, creating a transaction is something that can happen, or a request to create a transaction using this kind of sequence of instructions could be happening many times in parallel when different users are creating orders, and there also are like reads that are happening in parallel. So given all that, what I'm claiming is that we want these things to happen all at once, so that it's not possible to see the state of the system or for the system to be modified once we start the transaction until we get to the commit. Right, so we shouldn't be able to, for example, if we read from the orders table, we shouldn't be able to see this order row unless this order details row is also read. So why do we need these to be completed atomically? Think about that for a second. There are actually 2 different reasons. See if you can get both of them. Okay, so the reasons are, first of all, there's a race condition on this order number, and this was programmed in kind of a weird way. Normally, relational databases have built in the ability to have auto-incrementing values for certain columns. Like the order number could be set to auto-increment so that whenever you added an order, you didn't specify the order number, but it would actually automatically do the step 2 thing where it got the maximum number and added 1 to it. But in this case, we actually did it manually. But because we did it manually, this order number that's stored temporarily in memory, if this was happening twice in parallel, you could have 2 customers' order creation processes that looked at the table at the same time and decided they were going to use the same order number because they both looked at the maximum order number and saw the same number, and so they both decided, oh, the next one is this, right? if those happen at the same time, in other words, if once we actually execute step 3, we're fine because we've added the order that has a new higher order number. So if someone else goes back and checks for the maximum order number, they're going to see this new higher value, and that's okay. But if we kind of execute step 2 at the same time in 2 different places, we're going to end up with 2 orders that get the same order number and try to create an order with the same order number. Okay, that's called a race condition. The second issue is a inconsistency that can arise, where if we get past step 3, but we don't quite finish step 4, but then we do a read of the database. So for example, if we print out all the order information before step 4 finishes, what we would see is that this customer has an order because this row was created in the orders table, but that order doesn't have any entries because we did not yet finish writing the entries in the order. So we would see something that was incorrect. We would see an incomplete view of the orders of that order, which would give someone reading the database some wrong information. It's better to say that the customer does not have that order at all yet than to tell them they have an order and there's nothing in it, because that's wrong. It's true that in the past, the customer had one fewer order. That's a valid view of the system from a consistency perspective. It's not correct to say they have an order that has nothing in it. All right, so this transaction ensures that this first insert is not viewable until after the second insert happens. Okay, hope that makes sense. And I guess this also would be covered in the database class, of course. Now, transactions, I've said that transactions are kind of easier and more universally available on relational databases. They are less common on NoSQL databases because it's kind of slow to implement that synchronization to make them work. They're possible, and there's some databases that do support transactions in NoSQL databases that support transactions in some way or another. Mongo supports them pretty well over the past few years. They've added more and more features to support transactions up until very recently. Like, this is something that they've been working on very recently to improve. And Cassandra also supports it to some extent, even though it kind of goes against the basic design of the system. So to understand, let's break down a transaction into the simplest possible set of requirements. Basically, with a transaction, what we want to do is modify multiple rows at the same time, and not allow someone else to see just one of the modifications without the other ones. Or alternatively, that they don't all have to be writes. They could be like read and then write, as we saw in the previous example as well. The previous one was read, write, write, and the read and write, the first two had to happen together, and also the second two, the two writes had to happen together, and then the read and the first write had to happen together. So I was making a transaction that actually included two different things that had to be atomically together. Anyway, so for that example, to make that correct, what we really need to do is just make sure that no one else is reading or writing those tables or those rows at the time we're doing the modification. Like whatever data that we're reading or writing during the transaction should be unavailable to other users of the system at that time. That's the important thing. All right, so we can think of this as we can solve this problem by implementing some kind of locking. A lock is an operating systems concept that means that provides for mutual exclusion. So only if you have many users trying to do something and you want only one of them to be able to do it at once, which is kind of like a transaction, right? That's a generalization of a transaction. A lock lets you do that, and a lock is something that it's like a data variable essentially that can only be set, that usually defines who has access, and it can only be set to one value. And if the value is not set to your identity, let's say, then you can't do the thing that has to be done mutually exclusively. In this case, you can't access those pieces of data. Okay, so the general, and the next slide will give a little bit more detail on that, so bear with me if you didn't quite get it yet. So to make a transaction work in a distributed database, we have to lock the keys involved like the data rows or the data in general, to prevent reads and writes on those keys. And it's it's more difficult in NoSQL because you have a lot of replicas of that data. So all the replicas have to agree that that lock is active before you proceed. So the lock tapes involves a lot of communication. And you might have multiple competing lock requests in parallel on that same data. And they all have to agree on which one is chosen. So if you have two different nodes trying to come in at the same time to lock a certain row, then it could be that one replica sees user B first, and another replica sees user A's request first, and then when they tell each other to lock on their behalf, they're going to disagree about who should lock, right? Because they each got a request from a different user. So there has to be some kind of coordination there. It's kind of a distributed consensus problem in a sense. But in general, just realize that there are multiple rounds of communication that might be needed to agree. You can't just have, for example, have all the requests go to one place, which is like sort of like the master that dictates who is locked. That's not a scalable design. To make this really scalable, you have to allow this to happen in parallel on different nodes, and that introduces the possibility of disagreement and multiple rounds of communication to settle on an agreement on a final value. Okay, once we have acquired that distributed lock and the replicas agree to the lock, then we can execute the transaction on all the replicas. Like, we can take our time now because we know no one else is going to mess with that data. We wait for all the replicas to confirm that the data was like written, or that we got all the data from all of them, and then we can unlock the keys involved, and that lets other users who are trying to read the data to proceed. Okay. Well, the database has to support this kind of locking. And there's a paper from Google in 2012 in OSDI, which is a very well-known operating systems conference, that covers implementing. One of the things it covers is implementing transactions in the Spanner database, which is one of their big NoSQL databases. All right, so how to implement this distributed lock? Just like in an operating systems class, when you look at implementing a lock across parallel processes, you need some kind of atomic conditional write operation, which you might have heard of test and set or compare and swap or something. In this case, I'm supporting, this is actually a compare and set. But anyway, I need to be able to do two things at the same time in order to implement a lock. You need to be able to like check to do a test of what the value of a data variable is, and also set it if it's conditionally if it has a certain value or doesn't have a certain value. So the simplest way to think about this is where you have a value that's stored in a distributed database, like a key that is that's acting as the lock, and the value it stores is the identity of the client that's allowed to access the data. So to make that work as a lock, you need a single operation that checks to see whether that value is cleared. So this is shown in purple here. If getting the value of the lock is 0, so in other words, the lock is not assigned to anyone, then we want to put my own identity, my own number. In this case, like this is client 37 running this code. Put my own value, store it in that under that key. And these two things have to happen atomically at the same time, because again, there could be a race condition where if two users at the same time check the value of the lock and they both see that it's not being held, then they both might proceed and try to set the value to their own value. You can't let that happen separately in two steps. It has to be like that. If I see the value is 0, then that definitely sets my own sets the value to be my ID without allowing someone else to read it in between. And this is in a loop, because if I am not able to get the lock, then I should just keep trying to get it until someone releases it. Basically sets the value back to 0. So I have a two-step transaction here. This is a simpler transaction compared to the previous one, because I wanted to fit it in this half of a slide. But this is where it's like a banking thing. I want to deduct $1 from an account. To do that, I have to get the value of the account and, let's say, subtract 1 from it and then store the value back. Okay, those are two steps that have to happen at once. We don't want two users to come in and get two clients to come in and get that balance and then they both deduct 1 from it, and they write back that value, but then they think that they each deducted $1, but they each actually deducted $1 off the same value and came with a value that was just $1 less instead of $2 less. So these two have to happen as a transaction. Finally, I'm just releasing the lock by setting the value to 0. So how this relates to distributed databases is that if a distributed database supports one of these conditional write operations, where you can check a value and set a value conditionally, then it can support transactions. And Cassandra supports this. I also said Mongo supports transactions, although it has better support, so you don't really need to work at this low level of like doing these conditional operations. But if you look at the Cassandra documentation, it'll say that you should avoid doing this because the performance is slow. It involves several round trips of like data fetching between the different replicas. Okay. So you have the option in many NoSQL databases to do transactions, but there's a cost to it. So if you need to do transactions, if you need to support transactions, then some applications don't require transactions at all. One reason you may not. Keep in mind, NoSQL databases often store a lot of related data under a single key. So if you have this big JSON, like in Mongo, if you have this big JSON object that's stored under a key, then the fact that two parts of it change at the same time is not really a transaction, because the thing that you're storing is that you could be storing just like changing that whole document at once. It's not. So if you're storing a lot of data under a key, then you can avoid transactions by having the related data under the same key, right? But if you do need to modify two different rows at the same time, two different keys, then you can use one of these NoSQL transactional operations, or you can switch to using a SQL database and know that there's good support for transactions there, although it's less scalable. Or you can do kind of in-between thing, two different in-between options actually. You could say, okay, some of my data, like the accounting part of it, the part that deals with dollars and cents, might be more sensitive to transactions. So that part of it I'm going to store in a SQL database, a relational database. But then other parts of the data, like product information, like the bigger parts of the data that's getting more reads or writes, the part that needs to be more scalable, I'll put that in a different database, and that'll be more scalable, but I won't be able to support transactions there. So you might have a split between. It's very common to have a relational database and then one or more NoSQL databases, and to split your data according to both the size and the need for transactions, and also the need for consistency. There's more consistency on the SQL side. Finally, you could also potentially use like a variable in the SQL database as a lock and use that to control the transaction, the concurrent access to something in the NoSQL database. That's a little bit hacky. Okay. All right. So we were just talking about relational databases, and we mentioned, because transactions came up, we talked a little bit about how transactions are implemented in these other more scalable databases, the distributed databases. So we look at these different types of data stores. Some of them are more scalable than others, and the ones in the middle are the more scalable ones. These are the ones that use some kind of data partitioning method, such as hashing, like a distributed hash table, to get like almost perfect horizontal scaling. The relational databases don't have that same automatic scaling, and networked file systems, which I'll mention at the end, are another data store design that relies on using one machine and is less scalable. But let's focus a little bit on all these different scalable choices in the middle and what the differences are. The key difference I think you'll find is in the way that data is abstracted and stored. So the format of the data as it's stored in the database. Okay. There are many different ways of formatting data, and different data stores make different choices to meet different use cases. So with relational databases, of course, we have tables, rows, and columns that are highly structured and that have links between them. hopefully that's relatively familiar. For these other data stores, there are two big categories. The first one I'll call semi-structured, and the second one I'll call files. Okay, so files are maybe an easier concept to understand, so just to mention that first, I'm classifying distributed file systems on the bottom with NoSQL databases in the middle. I'm classifying those, I'm calling them both data stores because for many, they both offer persistence, they both offer large capacity, they both offer scaling, so they really do offer like very similar kinds of solutions. Like they can be used to solve the same kinds of problems, but the data abstraction is very different. So with files, we have a file name and we have the data. The data is a blob, like a big, just like a bytes, zeros and ones. The way that you access a file system involves specifying the file, like giving the path, which is the key, kind of. So you can think of it as a key value store. The key is the path. The value is the contents of the file. Okay, but that value is just a big chunk of data. Now, of course, all files have some kind of structure to them, right? And the program has to know what that is and interpret it accordingly. So if you have a data file that's .html, it's an HTML file, and you open it on your computer, your OS will look at the extension, say, oh, this is an HTML file. It'll open it with a browser, and then the browser will know how to interpret that to render a web page, right? If it's a text file, it'll know that you should use the ASCII encoding to decode it, maybe, or UTF-8 or whatever, and there are characters in it. It could be a JSON file, it could be an XML file, and you could store complex data in there that has its own structure in that file, right? But I'm ignoring that structure that's available in the files because from the perspective of the file system, and when you're using the file system, the API that the file system provides is totally ignorant about those internal structuring details. All the file system gives you is the ability to open the file and to read. It's like basically scan through that data and read it byte by byte, or chunks of bytes at a time. And then you, in the application level layer, have to implement any logic associated with like parsing that file, right? Okay, so the storage API is not aware of that internal structure, and there's no way for you to make use of it. Like for example, if you have a JSON file that's stored in a file, there's no way for the file system to like modify just one of the key value pairs, like to store a value under a key. The file system doesn't know how to do that. So you could write some Python code that used the JSON library together with the file system operations to do that, but you're implementing that at the application level. And it may not be as efficient as if the file system the file system itself knew about JSON and knew that the data you're storing was JSON and could actually like find that data more efficiently. Okay, but these other databases generally are not just key value like blob stores like file systems. They actually have some structure to the data. They impose some structure to the data, or the database is aware of the structure of the values of data and allows you to kind of like use it in some way. But the exact choice of what that structure is different for these different databases, whether we're talking about search engines, document stores, Redis, or something like Cassandra or DynamoDB, which is a kind of a traditional NoSQL database. Okay. And we'll go through these semi-structured options now in a few slides. Okay. So depending on the data you're storing and the way that you're modifying it and how it's being accessed, you would, and also how big it is, you would, I guess, want to choose probably from among these. You'd make a different choice of which of these kinds of NoSQL databases you would use. I guess I'm labeling Cassandra as a NoSQL database, but NoSQL is kind of a broad term that kind of also includes these other ones. But anyway, yeah, that's just terminology. All right, so some of what I'm showing is described also in this article. Let's start with Redis, because this is in some ways one of the simplest of these distributed NoSQL databases. Redis is a key value store, right? So the keys are hashed to figure out which of the replicas not which of the replicas, which of the nodes stores that data. But the value is not just a blob like in a file system, but it can be one of several different types. Like there's certain types that are like available in Redis that you can specify to store the data. So you can store strings. Strings are like maybe the most generic kind of data. You can encode almost anything as a string, right? But you could be more specific, and like instead of using a string to store data, you could store explicitly a list or a set, let's say, of data. Then you'd have many elements that were stored under the key. The advantage of this, of course, you can represent a set or a list as a string, right? Like you could use JSON to represent a list. You could use something like JSON to represent a set. But if you were using the string data type, then the database would just allow you to get that string and set that string, maybe set a substring like according to character positions. But the database wouldn't really be able to do anything more sophisticated with that value. However, because Redis supports all these different types, it gives you some additional ways to like access and modify data according to what type it is. Like for example, with a set, if you store a set under a key, then Redis gives you operations that are specific to a set, like add an element to a set, to this set, right? So you give the key and you give the value that you're adding, and it will find the row. There'll be some set there probably that has many entries in it, and the value that you provided will be added. So with the logic of set is that if the element's already there, then it won't do anything, or it'll overwrite it, I guess. Or if the element's not there, it'll add it, right? So there can be one of each. There can be no duplicates in a set. That's handled by the database internally. The application just provided the element to add. It didn't have to do the work of, like if this was implemented with a string, you could also implement the same thing, but you'd have to get the string. So that would come back. So there'd be an extra round trip there. You'd fetch the string that stored the set. You'd parse it. You'd check to see whether there was a duplication. And if not, you would add to the string. And then you would store that string, right? So there's a lot more work there involved in implementing a set on top of a string, which is what we'd get. Like if we were using a file, for example, to store a set, that's what we would have to do. Whereas Redis knowing about sets, like I said, it allows it to be implemented efficiently, much more efficiently. And the same thing goes for all these other types of data structures have things you can do to them, and those operations are available in the database without you having to implement them on your own. That makes them more efficient, both because of lack of less data being transferred and the modifications happening directly where the data already lies. Okay. Another feature of Redis, which is not really, this is just a design decision they made based on like what it was originally designed for. But anyway, Redis is designed to store most of the data or all the data in RAM, so in memory of the system, rather than on disk. I mean, it's backed up to disk so that if the process is ended, you have persistence. Optionally, it's not required. But so the original use case for Redis was for a high performance cache. This is why it's called a cache. If you have, for example, a distributed or like a web server that's implemented, like let's say Wikipedia, if there's a caching, the actual implementation of Wikipedia has caching on the front end with squid proxies, but you might instead implement caching inside the application itself. So where the application usually does queries to a SQL database to get articles, it could cache those results in a Redis distributed in-memory cache as an alternative way to reduce the amount of traffic to the SQL database. And by making sure that cache is stored in RAM, not on disk, it makes it higher performance. But it also means that it has to be a little bit smaller, a lot smaller. It has to fit in memory. Okay, so it's a NoSQL database, but it's usually referred to as a cache. It's used for fast storage for a few different kinds of data, but it's generally like a key value store with different values that are available, and yeah. So here's some more details. I'm not going to go through these specific details. These are from that article I linked to earlier. But I mean, I guess you can notice, without going to all these details, like there are a lot of like little features you can choose to build into a database, and this has some of those features, and other databases have different ones. And I think this one is written in C, and it's fast. One of the reasons it's fast is because it's written in C, but a database doesn't have to be written in C to be fast. The protocol, the API for it is like sort of a it's not a standard REST interface. It's its own kind of custom protocol for efficiency. Okay. The second database I'm going to talk about here among those NoSQL databases is Cassandra. Cassandra is maybe the most typical of NoSQL databases that we're going to look at, most traditional and most scalable. Although it's not just a key value store, but it kind of almost is. It's actually a 2D key value store, two-dimensional key value store. So you have a row key, and the key has a value, but that value is a key value store is a map, okay? And that the keys within that under a key are called columns to avoid confusion, but these are not columns in the same sense of relational databases. They provide a similar function as columns in relational databases, so it allows different kinds of elements, different pieces of data to be stored in a row and all be associated with each other. But these columns can be different for every row in the database or in the table. So you don't have to define these ahead of time; these can be dynamically added. So this kind of blue circle thing, this row is stored. The row key is hashed to find which of the replicas stores this row, and this is stored on one node. It's also replicated in a couple other places depending on what replication level you chose. But then all of these column value pairs would be stored on the same machine. So this is like on one machine. But these columns can get very wide and big, but not like so big that they don't fit on one machine. To support these getting really wide, there is indexing within this structure. So basically this row key points to like a hash table or a tree map or something, to make it easy to, for example, if you're only reading the value of one column in this row and this row is really long, the database doesn't have to scan through all of these columns. It can quickly find a particular column and get that one value. Okay. So here's an example of data that might be stored in one of these Cassandra tables. You'll notice that columns are different for every row. I mean, in this case, there's a lot of repetition, but for example, birth date is not present in all the rows, and there's no problem with that. Like, there's no wasted space, for example, down here with the third and fourth row. I think these are cartoonists. I don't know where this came from, this example. Yeah. And this article here actually is really good if you want to go into the details of using Cassandra, like how to make this design work for an application. eBay has a really good blog post on how they use it, or gives some best practices for using a 2D key value store. Okay. Here's another example of how Cassandra can store data. This is data for bridge information, so it's a civil engineering data set. This is from a research article that I just found randomly, where, they're storing information about bridges, and this includes, it's like they have one big table basically with keys, and the keys have different meanings, basically, or correspond to different kinds of objects, and so different columns are stored underneath the different keys, and those, this can be different for every row, but generally they're different classes. So this one here, like these two objects, have some geometry information, probably for the bridge. So there's like XML code that's stored under these columns. All of these columns. This can be made very scalable. If you need to, you could have like an ID number in one of these columns that refers to another key that lets you kind of link things up, but that joining would have to be done manually by the client. Like, you can't automatically and efficiently get data together because it's a NoSQL database. Okay. So Cassandra, I guess you can. It's the most, in my opinion, the most generic of NoSQL databases. DynamoDB is another example. So DynamoDB is similar to this, and this is available. This is like Amazon's managed NoSQL database that you can find on Amazon Web Services. Cassandra is like an open source project, I think started by Facebook, that you can download and run on your own. It's really scalable, and it's great for huge data sets. It's scalable because it doesn't try to do any fancy indexing aside from the basic distributed hash table. Like the columns are indexed internally, but that's like within a single node. There are no secondary indexes. So other databases like Mongo try to be a little more clever, and Elasticsearch with lots of indexes, even though the data is distributed, and that limits the size a little bit. But Cassandra doesn't do that. Okay. So again, also some interesting details. One thing about Cassandra is that it handles writes actually really well, and even better than reads, because it uses an append-only data structure. Like it adds data to the end of files rather than having to insert it into random places when you do modifications. So it's kind of a log-based storage structure. But those are like details. So like all of these databases have differences in the structure of data that's stored, the way you interact with it, but also there are a lot of like design decisions internally that affect the performance. And so you have to kind of trade off all of those things, I guess. But you're never going to be able to find something that's perfectly matches what you need, so you kind of choose from what's available. All right, so the third example I want to talk about here is Mongo, which is a very popular NoSQL database. This is most often called an object store, or I guess a document store. So it's a document store because the data it stores are JSON objects. You can think of those as documents. Okay. And there's one key in the document that's the sharding key that's used to determine what partition the data lives in. So you can use that to efficiently find this data. But then the data you store is JSON, and then again, because the value is not just a blob, but it's like the database knows it's JSON, so you can query using JSON features. Like you can query for just the value. Like if you just want the death date of this guy, you can include that in your query, and the database will understand that and just get this one value and return it back to you. So Mongo also has a nice feature, which is that it keeps track of a history of changes. So if your data is in JSON, which is actually going to be common if you're doing development in, let's say, Java, and you're okay with like storing your data as a big JSON object that has like kind of like a nested structure. You can change little pieces of it efficiently with Mongo. You don't have to rewrite the whole document. And Mongo will also keep track of a history of changes if you want that, which is nice, which is, kind of a cool feature. So but it's less scalable than Cassandra. So it's a kind of, for many web development projects and development projects in general, it's a default choice. If like you want a decent amount of structure, but you need more scalability. So the structure you get is by defining these JSON objects. And you get the ability to just work on little pieces of it efficiently, of those JSON objects efficiently. Some more details here. All right, so the fourth example I'm going to mention here is Elasticsearch. Of course, you use this in the homeworks. It's kind of similar to Mongo in the sense that what you're storing is a bunch of documents that are JSON documents, or that are formatted in JSON. And those documents are shared across the nodes somehow with some kind of hash-based sharding. But it provides a very different kind of indexing and query interface than Mongo. So it really fits a totally different kind of use case. So Elasticsearch is designed to index every single word in the document and allow you to efficiently find documents. I mean, you saw in the homeworks that you could type things in and the database would just like give you back thousands of results very quickly. I mean, I guess I don't know if you realize this, but if there wasn't indexing and there was tens of gigabytes of data being stored for all these articles, more than 2 million articles, to actually scan through those 2 million articles would take a long time, would take like hours probably. yet you're getting results in like in milliseconds or even microseconds if you had low network latency. So the way that could happen is with indexing, but there are a ton of different words in here to index, right? So it's one thing to index this thing on just the one key. Like for example, if we just use the URL as the sharding key, and we always had the URL available when we wanted to fetch this data, that would be a very simple, easy design. That would be like we could handle that with Cassandra or Mongo very well. But the user, you would only be able to get this data efficiently by providing the URL, like whatever that one primary key or hashing or sharding key is. What Elasticsearch gives you is indexing on every single word of the document, and the ability to construct queries that are like that use complex rules, like for example, combining two different words, or like parenthetical things like this and this, or this and this, or this or this and not this, things like that, negations. So I want you to actually take a moment to think here, and take a couple minutes if you need it, because this is a really good thought exercise. Try to figure out how you would design Elasticsearch using a very simple distributed hash table, like let's say Redis or Cassandra, or even something simpler than that, where you just have a key and a value. How could you implement this feature where we index every single word in this document, and we could fetch this using any one of the words, but the building block we have is a distributed hash table, right? And so a hint for that is, if you don't want to think about distributed systems, just think about doing this in Python, let's say, or Java, or whatever. And the thing you have is a hash table. Okay, so a hash table, a distributed hash table are the same thing. They're just one is on more machines. We showed that how it's easy to build a distributed hash table, but the API is a hash table, right? So if the building block you have is a hash table, you want to be able to do query like Watertown and gift, so 2 words, give me all the documents. How would you use hash tables to implement that without having to scan through all the documents and like check them, but like quickly find them using the hash tables? Okay. All right, so hopefully you thought about that. The solution is called an inverted index. So what this means is that you have a hash table where the keys are words and like all the words in the language, and in particular every word in the document. So you would still store this under a key. So this would be stored under, like, let's say the URL, right? So this value would be stored under the URL, but then you also would store in a different hash table, let's say, or the same one with a different like prefix or in the key to like distinguish it. You would take every single word in this document, and you would use that as a key and store as the value this URL. So for example, the word owner here is a word that appears in the document. That could be a key in the hash table, and that would map to this URL. Now, of course, owner is a word that appears in many articles. So you actually would need that key to map to a list of all URLs of documents that have that word. Okay. So you could go through and like every time you add a document, you would add the document. You would also go through, break out all the words, and add to all of these words to those hash tables. So to that hash table, you take the word as a key and store as a value, add to the set that's stored there this URL. Okay. So for example, if you're using Redis or Cassandra, either one, you have this sort of like 2D structure where you can efficiently store a set, in the case of Redis, or a set of URLs under each word, or you can store a list of columns, which is kind of the same thing. The columns in Cassandra, let me go back to that. These columns, you could think of these keys. So a map is kind of actually a generalization of a set, where you have not just the key. Like a set is just a map without values. So the column names actually form a set in Cassandra. So you could use those to represent all the URLs, and they could be made unique and also efficiently accessible using that indexing that I mentioned is built in for the column names. Okay, I hope that made sense. That's pretty cool. Maybe a picture next time would make that more clear. All right, so this is Elasticsearch is called a search engine. It's still a NoSQL database, but has a specific purpose for full text document search. Okay. All right, so finally, the three other storage options I have here are all file systems, right? So these are for storing arbitrary data. The structure of that data is not really known to the file system. The file system operations can't like parse the file and do interesting things with it, but you just get these kind of blobs of data available. And but there are different variations of those I'm going to talk about. Sorry. The first and simplest one, and probably the least important for scalable systems, is a networked file system. But this is like a step toward a scalable design. So the networked file system, you may have seen on like your Windows machine that you have like file sharing available, where you can have the files on one machine available to another machine on your network. That's the idea here. We have an application server that has some code in this green box that implements your service, and to persist things, it uses some files, right? So like instead of a database, or in addition to a database, it also has some files where it stores things like maybe they're images that it needs to serve back in a web page, or it could have a text file that lists out all the customers, whatever. Like that, you can use the file system in your code to store things, right? Now, the difference here is that we have some files that are stored, and most files you would think of are stored on that machine, like on that disk that's in the machine. Like this is showing a file in the home directory. But you can also have the operating system set up some special folders in the system that are mounted or mapped to a remote file system. So you still use the same interface, like your program still is just opening a file path, the same as a regular file on your system. But the operating system is translating that, instead of translating that to a location on disk locally, it's translating that into a network request that fetches data from another machine. Okay, but the interface to the application is the same. That's the important thing. The application opens files, closes files, reads from files, writes to files, like byte by byte. And it can scan through the files, right? Those are the things the application can do. The code for doing it is the same whether the application is working on a local file or a remote file, as long as the system is configured with a networked file system at the operating system level that knows where to connect to get that file. So this is showing some kind of like a file server, which is a machine that's specifically designed to provide files to other machines, and it probably has a lot of disks in a RAID configuration to work in parallel and with redundancy. And this file server could be providing data that's shared by many app servers at the same time. Okay. So this is a valid design. It's not super scalable because the file server is one machine, and concurrent access is, mainly because it's a single machine. The advantage here is that if you design your system already to work with local files, you can easily kind of scale it out to work with bigger systems. You also can use a remote file server to host. Like internally, if this is actually implementing a database, for example, it might be a useful design to have like what's called a storage area network, where you store the database's contents actually in another machine, maybe. Anyway, but that's a networked file system. And on Unix, there's an NFS protocol for doing that, networked file system. On Windows, it's called SMB, which is like shared something blocks. Okay. That's kind of a traditional design, and it's not very scalable. A more scalable variation of that is a cloud object store, which is essentially a general purpose file store in the cloud. It doesn't have to be in the cloud, actually. It could just be on your own hardware, like locally. But the point is it's on a distributed set of machines. And in this case, we still have a bunch of files. So the interface is kind of similar. We explicitly have keys and values, and we don't, like at the application level, we're not using the file system, the operating system's file system interface to like open files and close files. Instead, we're using some kind of network API similar to accessing a remote database. So you might be using a REST API to access this remote file system. So an example of this is S3 from Amazon. And remember, we used this in the first homework to access the work files that were stored by Common Crawl. Okay. So, those files were not on, you couldn't in your terminal see those files in your file system. It was some kind of weird remote file system that had to be accessed programmatically through an API, and we used a library for that. But the data is kind of stored in the same kind of way. And this kind of design can be made scalable by deploying this over a distributed hash table. Although as a user, when you're using this, you often will be using a managed service like Amazon S3, where you're not actually... Somehow Amazon gives you the illusion that there's unlimited capacity in their system, and you can just create folders, which are called buckets, and store files, and use a network API to access it. Of course, behind the scenes, Amazon has a certain number of nodes, thousands, of course, or millions even, and they have to add more machines when necessary, and they kind of probably have split it into different partitions so that they don't to make it more manageable. But that's all kind of hidden from you as a programmer. Okay, so this is called an object store, or you could think of it as a distributed file system. One interesting thing about these is, of course, the API they provide, the interface they provide is different. It's not an operating system file. You can't go to Windows Explorer and see the files that are in your remote file system. It's more of like a network-based API. But there's also, so it's harder to use in some sense, but also for some use cases, it's easier to use because it provides an interface that's more directly accessible to, for example, web browsers. So in the case of one of the pages on my website has some research data from one of my research projects in grad school. And so this is a little snippet, little view of a web page. And I have links to some data, like some audio recordings that are pretty big, 4 gigabytes, 4.4 gigabytes. So because these files are huge, I didn't want to store them on my little tiny T2.micro web server. Instead, I store them in Amazon S3, which gives me unlimited capacity, and it's separate. It can be kind of accessed from anywhere. It's not tied to one machine. And in the HTML code, you can see that I have links to this data, and the links for the small files I put directly on the web server, and therefore the links are the same. Basically, it's like stevetargia.com/localization/mobisys11 batphone, whatever. This is like in the same location as the HTML files. But for these really big files, I have links that actually go directly to S3. So you notice that the domain here for these links to these big files is s3-us-west-2.amazonaws.com. Okay, so this is actually, S3 has a sort of a public HTTP GET interface available to access the contents of these shared file systems. Now, I had to explicitly enable public access to anyone without authenticating on these files, but that was my intention, because these are open data files. And this is kind of similar to what Common Crawl provided. The way that Common Crawl is sharing their work files is the same as the way I'm sharing my audio recordings from this research project. And I actually have a link on my website that allows your browser to download directly from S3 those big data files instead of having to go through my web server. And so this is a common, if you look at web pages, you'll often see these like S3 Amazon domains in media files, like images, videos, things like that. Very often those will be stored in S3, and then the access to them will be provided directly through this S3 domain. All right. The final kind of storage system I want to mention just very briefly is that Hadoop file system and systems like that are distributed file systems that are designed explicitly for these parallel processing systems for big data. And I don't have much here, and it's kind of difficult to explain, but you can think of it like S3. It's a distributed file system. The data is split among many machines, but the interface for it, it uses a specific format that works well with the particular parallel processing tools in Hadoop or Spark. So this allows the processing of data as you define in your Hadoop or Spark job to be run on the data nodes, so that you don't fetch data, process it, and then get a result. What you do is you give your analysis to the file system. The file system runs the analysis. But it's not just a file system, it's a special file system. It's the Hadoop file system that has a combination of a file system, but also this like platform for running complex compute jobs at the same time. So it's a weird mixture. It's a very powerful kind of system, but also difficult to use and a little difficult to understand. So hopefully we'll come back to this in later lectures when we talk about really difficult big data processing tasks. So like actually so far the kind of scalability we've been dealing with is like independent transactions, and it's much easier to deal with that than, let's say, taking all the data on Facebook and doing an analysis of like figuring out answering some research question like do are users seeing content that is appropriate for them or something like that, answering some kind of general question that requires analysis of all the data at the same time. It can't be like trivially parallelized. A better example maybe is like taking all the purchase history in Amazon, like figuring out a set of recommendations for, given you bought a certain product, what other product should you buy? That depends on everyone's purchase history. Okay, but again, that was a little bit light, and we'll try to get more into that later. So as a recap, here are the different storage systems I mentioned, different kinds of databases, although some of them are file systems, but I like to think of them at the same time as databases because they solve the same kinds of problems. There are many trade-offs. Often they involve different kinds of storage structures. Earlier slides had a summary of the different storage structures for these databases, different levels of scalability. Relational databases support transactions. You can kind of get those on relational database on a NoSQL databases, but it's kind of slow. And file systems provide a more kind of like coarse-grained abstraction of data, but they have their uses as well. All right, I hope that made some sense. See you next time.